So what is Akka, and why are we talking about this? So one of the things is that it is a platform for next generation event-driven, scalable, and fault-tolerant architectures on the JVM. The key points to note here are event-driven, fault-tolerant, and scalable. These are the things that most of us struggle with most of the times. That we are not able to build systems which kind of are parallel enough. They are concurrent enough. They can scale well. Whenever we get into kind of developing any kind of a product or a project, most of the times we are focused more on the functionality. That let's get this functionality out, and then later on the performance and other things would kind of follow. Now, one of the reasons for that is that had these things been very easy, then in that case we could have just started focusing on them outright. But these things till date had been kind of very difficult. They are still quite difficult. But we are just trying to kind of make leaps in front so that we can kind of have some platforms, have some infrastructure which can make things possible for us. So for example, if you were slightly attentive in the Scala discussion yesterday, you would have seen that there are certain methods through which we can actually tell the library that I want this particular functionality of mine to run on all the cores of my machine. What is that? Remember? Power, right? So as soon as you say something like that, now that is where the inherent library comes in, and it makes the task much easier for you. Now Akka has tried to take that a level further, and what does it do? So first, what is Akka? It is an actor-based concurrency framework. Anybody has heard about actors? Great. Oh, okay. Lot of. Okay. Not the film ones. Yeah. Okay. And it provides solutions for non-blocking concurrency. It is written in Scala, but it can work on Java. So that is the beauty of it, that it is written in Scala. The entire code is in Scala. So if you download the code, it is all in Scala. But they have provided library and kind of APIs for you to use it in your Java application as well. So it just becomes very easy to wrap it inside your Java application. This weekend they are supposed to be releasing a 1.3 RC2. Till date, what you'll be seeing on the site is 1.3 RC1. We are closely kind of working with the Akka guys on some of the aspects. So 1.3 RC2 would have some of the bug fixes that would be going in. And for example, have you used RabbitMQ as your messaging system? Any of you? So RabbitMQ keeps coming on with kind of various plugins for kind of exchange, so consistent hash and other things. So that is something that they'll be incorporating in this release. So how was it developed? So the lead developer and the co-founder is Jonas Bonnier. He's the person who was kind of behind many things like JRocket, AspectWorks, Terracotta, if you have heard about that. So it's coming from a strong community which was kind of strongly into JVM and trying to make JVM kind of more scalable. So any of you have used Terracotta or heard about it? Okay, great. So it extends your kind of it makes your multiple JVMs extend, and you can share the JVM heaps. So it's coming from that community. The issues, as we talked about, that we face right now are kind of these three big issues: concurrency, scalability, and fault tolerance. And this is what really Akka attacks, or wants to kind of attack and makes it very simple for us. It provides a very simple concurrency. It is event driven, and the key to note here is that since it is event driven, you could use it for real-time processing. So as soon as an event comes in, you could kind of just grab that event, process it, and it goes further. So for something like getting a lot of feed in, something like maybe Twitter feeds, this is the system that you would be using to do real-time processing. It can interface with the likes of Hadoop, where you can do batch processing, right? So you actually kind of do event-based processing, then you actually kind of move it to the batch, and then Hadoop can also do batch processing for you. But the key difference is that this would help a lot of event-based systems. Hadoop would help a lot of batch systems. You could kind of use this for batch systems as well, but that is not where it kind of really fits in. What it supports is a scale up and scale out. What do we mean by scale up? Is that I could potentially be using all the cores. I could be using a heavier hardware, and I could be kind of deploying my application on all the cores, and it just kind of works. I could be scaling out as well. I could be adding multiple nodes to my application, and it scales out. Fault tolerance, this is something that we'll look deeply into. Remoting. By what remoting means is that I could seamlessly, transparently pass on my work from one node to another remote node, which is kind of sitting anywhere, and my application just continues to work the way it is. So it supports distribution, and it has a Scala and Java API. We would not be talking about all the key things, But one of the very key thing which is present in this is the actors, which is being used extensively. And some of you have already used actors. But what actors are, if you just want to kind of relate, they are just like your potential Java objects, for example. Except that they are supported with something called a mailbox, right? What happens is that you can send messages into a mailbox. As soon as I get a message, I'll process that message. You could send up the messages and form a queue. So there'll be kind of multiple messages lying in my queue. And as soon as I kind of get hold of a message, I'll start processing that. So that is what makes it event driven. It is a message passing concurrency. They do not share state, which is something that you would always require for a scalable system. Whenever you start sharing state, that is when your scalability is lost, or you get into kind of multiple things that make it less scalable. They are very isolated and very lightweight. Communicates through messages. You can't see the last time, but that is asynchronous and non-blocking. So I can pass on asynchronous. They are not blocked. They process the message, and then it goes further again. Okay, but where does this actor thing come from? Actually, it's a very old concept. Maybe prior to most of us who were even born. Like I was born close to this, 74, but for most of you, it was much earlier. Carl Hewitt was the guy who introduced this concept. Erlang, heard about Erlang? Functional programming language? Great. So Erlang has actually popularized this concept a lot. So there are actors, there are mailboxes, and all of this actually comes from Erlang. It actually kind of takes away the pain from the developers to actually kind of look at threads, look at blocking, look at kind of various other things. So it just makes it much more simpler. How does it actually work? So for example, if you consider this to be an actor, as I told, would always have a mailbox. As soon as a message comes in, now an actor can do multiple things on that message, on the basis of that message. It could either do kind of some local processing on that, based some kind of local decisions. It could actually spawn off new actors, and these would be as good as this actor. They'll have a mailbox of their own. They could kind of correct messages, or it could kind of just spawn more messages. You can just think about the processing that you want to do with that. So think about it as a fact that you have a local queue in your system. There are these actors who are sitting. You pass on a message to an actor and it starts processing. Event driven, and it is kind of asynchronous, and multiple of them running together to give you the parallelism that you need on a multi-core box. So it just makes it kind of very easy to write concurrent and parallel systems. Let's look at okay, before we get there, actor models are of two types. So for any processing to happen, right, you need threads. And actors could either be thread-based or they can be event-based. When the actors are thread-based, what that means is that my actor is actually talking to an OS thread. So when that happens, it kind of becomes slow, because there is a one-to-one or kind of a many-to-one mapping, but I always hold a thread for my processing to happen. What happens when it is event-based is that they become very lightweight. They actually work across not a thread but across a pool of thread. So just assume that it's a connection pool and I've got a thread pool. Now what an actor would do is that I have got, I can actually spawn 6.5 million actors on 4 GB of RAM. So that is what I do on this box. So it could be, kind of these many actors. Just imagine, these many actors just, kind of present in your heap, and they'll be just waiting for messages to come in, and they'll be just processing those messages. And if you have 4 cores on your machine, ideally there'll be, kind of 4 threads running, kind of in parallel. Except if you have kind of a hyper-threaded CPU where there will be 2 threads per core, but then you'll be having 4 threads, and each actor, what it will do is that it will pick up a thread when it needs in an event base. It gets an event into the mailbox. It picks up a thread, does the processing, releases the thread back. Picks up another one, and then there are kind of multiple threads between 3,000 to 6,000 threads. Yeah.
The major difference that you have a pool associated with a large bunch of actors in the event is not or is it something?
So the question is that a major
thread-based actor?
Right.
Yes, is one thread per actor associated.
Right. So yeah, what happens in a thread base is that there isn't a pool. It is not backed by a pool. So there would be X amount of threads, and there would be kind of Y amount of actors. But the actor, as soon as it is kind of processing it, it will just keep a hold of that thread and it will not release it. So that is why for some systems maybe it is required. But when you are going in for like scalability, for those kind of systems, you'll actually kind of always go to the event-based route. there is a thread pool, and you just kind of pick up a thread, do your work, and release it back. And that is what gives you kind of massive parallel processing power. Just imagine kind of 6.5 million on 4 GB RAM, and this is something that you could run just on your commodity hardware. So kind of close to what we were talking about, I would have kind of quad core here. There'll be approximately 4 threads, but they are being backed by kind of millions of actors. I could just say that okay, there'll be say 3,000, a pool of 3,000 threads. Now all 3,000 of them cannot run on the core just together. They are time slicing, right? So there'll be 3,000 threads. Now as soon as the time slice, one would go in, one would go out. But then these are being backed by kind of millions of actors, which are getting messages, and these messages are being kind of processed by the actors by pulling a thread out and pulling a thread. That's it.
How event-based actors are similar or different from Node.js kind of concept?
Okay, see, that's a good question, and there is a kind of a strong argument. They are quite the same. I won't say that they are exactly the same, but they are on the right. They are on a parallel track. So there was quite a discussion, like in the community, whether Node.js is something that could be used on situations where we are trying to use Akka. So possibly yes. I don't know. I haven't evaluated Node.js enough. But what I've seen and what I've read is that Node.js would be giving you something similar, except that it would not be backed by the strong JVM support of kind of Java or anything else. So for very stable applications, probably that might not fit the bill. But again, there is still a debate going on that. But what you're saying is right. So each actor right now, like on the JVM, one thread gets a stack space of around 1 MB. An actor just kind of occupies 650 bytes. So that is what kind of makes it readily available within a small amount of RAM as well. How do you actually define an actor? See, the definition of an actor is pretty simple, and I've kind of chosen one of the simpler examples. It's only that you'll be extending an actor. So this is Scala code, but you'll be kind of writing a similar Java code. Okay, it'll not fit in this page, but it'll be Java code. So what will happen is that you extend an actor, and the only method that you define here is the receive. And what does the receive do? As soon as I have a message in my mailbox, I'll receive it and I'll start processing it. That's what it does. Don't go too much into the syntax, but I'll just explain it to you. It is pattern matching in Scala. What pattern matching does is that on the basis of the message which is coming in, I just try to see what kind of message it is. Is it a case string test message? Then okay, do this. Case underscore is like for everything else, like the default, do this. That received an unknown message. But this is how concise the code gets. Now all your logic that you want to kind of put, you might want to spawn new actors, you might want to kind of send out messages, you might want to do something else. All that logic you could just write here, depending on the case that you want to catch, and that's it. That's pretty much an actor for you, and that's an actor which can be a kind of concurrent. It would be running on multiple nodes. It will be doing all the other things that you want it to do. An actor lifecycle is that you would just create an actor and you just start it. So as soon as you start it, it has a mailbox associated which gets kind of messages in the queue, and then you can of course kind of shut it down and it's done. Okay, so this is how messages are passed on to an actor. So what you see here, exclamation mark, this is actually called a bang operator. And had we, so today we'll be having that DSL, yeah. So you'll hear more about that. But this is something. So this is a method for now. What to an actor, we are actually invoking a method which is the exclamation, which is called a bang operator. And what we are saying is that just pass a message, and that is just how simply a message goes through. It has been made in such a way so that it just becomes very easy to understand that how to kind of pass a message. So there are kind of 3 kinds of these methods: bang, 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 and triple bang. So that is how they are kind of called. So the first one, what it does is that from any of your code to any actor that you have defined, just pass a message like this, maybe a test message, and just forget about it. You just go ahead and you do your own processing. It's asynchronous. You are not blocked, and it is done, right? You can just kind of go ahead. So you can just kind of just imagine that you'll be passing millions of messages to your actors, and then after that it is the actor's job to kind of get their stuff done. What this would do, the double bang, what this would do is that it would send and block. In certain situations, you might want to wait for a reply. So depending upon what you want to do, you will actually do a double bang. you'll say, okay, I'm sending an actor a message. I want the response back to proceed further. However, in this you can kind of define a optional timeout. You can say that, okay, I would just wait for 5 seconds. If it is done, otherwise I am doing something else. So you could kind of do that here. The third one is a triple bank. What it does is that it fires a message, and you can still continue to do your own work, but as soon as the value comes back, it will be populated in the variable that you're using. So for example, if I say val a is equal to this, then the next line would be executed after that. This will go out as an asynchronous request, but I don't have to be blocked for that. I'll just kind of get the value of a as soon as it is done. So there are callback methods which are called, and that is how. So the idea is that all your paradigms are supported. So for example, if you want to just send it and not wait, just do your own thing. Go ahead and do that. If you want to wait, do that. If you want to not wait now but still get a response in the future, that is also possible. So this is actually all that an actor could do. Simple enough for kind of yeah.
And so if you have ton of actors running,
Right.
you decide how do you
Not have to, but then there is something called an actor registry. So what an actor registry would do is that it will tell you that these are the number of actors which are running, and these are the ones in this state. So if you want to identify them, each of an actor also has a UUID. So that is a unique ID across all the actors. So you could identify it with that.
if there's a pool of actors running and externally I want to submit a job to this pool of actors.
Right.
Then I have to
There will be multiple of these actors which will be doing a similar kind of thing. So you'll be just submitting it to you just submit it to kind of anyone, or you just say that, okay, this is my. So there is a concept called supervisor as well. And you could say that I am submitting my job to the supervisor, and then it kind of round robins or whatever strategy that I want to use. So you could do that as well. Okay, how do you? So for example, here to the actor we are actually kind of sending a class message. Here to an actor what we are sending is tuples. Okay, tuples might be so this is again a concept in Scala that if I put braces and I put any number of elements in that actually creates tuples for me. So for example, this is called a pair. This is a 2 tuple or a pair. I could have comma anything else. So that is a 3 tuple. That is triplet. Or I could be kind of sending list. So you are just free to send any kind of a message to an actor. The only thing that you have to remember is that in the receive, you just have to receive the type of the message that you are sending. So for example, I say that in the receive, I'll be saying that, okay, case and of the type list, then this particular message will be executed. In the same receive, if I have something like, okay, kind of case and a tuple, then this message would get executed. So depending on the kind of messages that you are sending, you could just kind of define your receive cases as well. Okay. So we talked about actors. What actors give you is a lot of concurrency. They give you a lot of scalability. But what about fault tolerance? Now remember, these are 3 things that we are really concerned about: fault tolerance, concurrency, and scalability. Akka provides you a very kind of robust fault tolerance mechanism as well. And what it means is, we don't care, crashes would happen, so let it happen. That is the strategy. Let it crash. So because we are backed up with so many actors and we are backed up with kind of so many things, so even if it crashes, it's okay. I'll just process the message again. And that is essentially what happens. Like if you look at the for example, the eBay architecture, they don't talk about ACID transactions anymore. Like they have stopped talking about that kind of way back. They actually have something called base transactions, which is eventually consistent. I don't care if some of the transactions are failing or they're not completing the way they should. I'll just reconcile them later. And that is how the scalable architectures. So with ACID, it is very difficult to build a scalable architecture. Here, what they say is that, okay, crashes are going to happen. Let it crash. We don't care. We just kind of get to it when we get to it. So the support that is provided in that case is that for each of the actors running here, there is something called a supervisor. A supervisor actually supervises a set of actors, and these set of actors could be any number of actors that you want them to be. The only thing that you have to do is that you have to link the actor to the supervisor, and you say that, okay, as soon as my linking is done, now you can define your various strategies. Now once the supervisor has control of the actors, it can start them, it can stop them, it can monitor them. So through the supervisor also you get all the actors which are associated with that supervisor, and then you can define various strategies. So there is an all for one strategy, one for one strategy, but okay, sorry. So I don't know if you can read this, but I'll just read it for you. So you define the strategy that, okay, this is my all for one or this strategy. and what is the exception on which this strategy should be activated, and what is the maximum number of retries that I'll be waiting for, and what is the default time that I'll be waiting for. So that is all. This is how you define your strategy. And what does the strategy do? What an all-for-one strategy would do is that, so this is a supervisor, this is managing these actors. As soon as one of the child, dad dies, all the actors are terminated and the entire set is rebuilt. So for example, if you know that, like all this set of actors which are working, they are working on a certain kind of a computation or something that even if one of them is dead, I need to do the computation again. So you specify this strategy. That even if one of them is dead, you just go ahead and kind of just do the entire thing again. So this is how fault tolerance is built in. As soon as an exception occurs in one of them, the supervisor kicks in and it says that okay, or maybe the result is not going to be fine, and I'm expecting a better result. So let me just clean it up and restart it again. So then you get a restarted and then you get the result back again. However, for certain transactions, you might want to go for a strategy which is this, which is that okay, since one of them died and others can still go ahead and kind of give me results, I'll just kill that one and start that one again. So these are the two main strategies which are supported with supervisors, and you could kind of just adapt one of the strategies and depending on the need. But the idea is that it makes it very fault tolerant. You don't have to kind of really worry about what happens when it happens. You define the strategies, you define your actors, you define your supervisors, and you just say okay, one of this happens, do this. I'm not concerned. I'll still get back my result.
So in the previous case, so the messenger to restart the process,
right.
The messages are preserved so that it can restart it.
Yes. So the message, what would happen is that you'll be sending the messages to the supervisor. What the supervisor would do is that supervisor keeps the messages and it passes them on to the actors. As soon as it knows that something has gone wrong, it passes on the same set of messages again to the actors. So that is where the supervisor is the main controller. Any other question on this?
Does it in any way become a single point of failure?
Actually, anything could become a single point of failure if it does not have redundancy built in. So potentially what you would try to do is that you would try to kind of create some redundancy around it. So if you want to keep it high availability, you'll have multiple supervisors as well running on X number of actors. So then in that case it just becomes kind of a redundant failover support for you, and then it.
Configure it in a way which.
Yes, yeah. There are various strategies to do that as well. I'm not getting into that, but yes.
Would we prefer a 1-for-1 over all-for-one?
Again, depends on the scenario. Preference ideally for a scalable system would be kind of 1-for-1, because I do not want the entire computation to happen again. I would rather kind of chunk my computation in such a way such that if one of them is dying, I can just kind of recompute that part, and the rest of them I can still use the results. So you have to kind of make your architectural decisions in such a way so that you can actually make a system which can scale better. Because all for one, and if you have 1,000 actors and just one of them dies, and then you have to kind of rework the entire thing again, that will take time, and that will kind of take a hit on the performance. But there are situations where you would want to do that, so it will depend on the use case. Okay, another thing that is interesting is that you could have supervisor hierarchies as well. So there is a main supervisor which has got multiple supervisors under that, and you could go to any level. But depending on the complexity of the system, I would like to believe that we have built a, if not very complex, a fairly complex system with this, and we did not have to use kind of all this supervisor hierarchies. So depends on your needs. But the system that we had built that did not actually go into a lot of these levels. But depending on the complexity, you could as well. It is like it is supported.
One question. So there will be some lookup with supervisor while we doing right for distributing all the work to all the actors.
Yeah, that is a very good question, and that is something that we struggle with as well. So ideally, you just pass on the messages. Then there are different strategies that will kind of help the message go to different actors or different supervisor hierarchies. The different strategies could be round robin, it could be load balance, it could be kind of other multiple strategies. However, in certain situations, your distribution of messages not only depends upon your local JVM where you'll be distributing work, it also depends on how the work comes to your node. So we had to think about certain scenarios in which how the work would be coming to our different nodes. So we are running this platform right now on 40 blades, and there are kind of 40 such systems which are running. But how does the load get distributed amongst these faulty systems? So that is where we had more of a problem rather than this one. For here, you have some strategies which are already built in. So you could kind of define a failover strategy, you could define a load balancing strategy, you could define a round robin, and other various options.
Okay.
So what is basically a supervisor? Again, it's an object or the controlling object looking for.
That is correct. So it sits over the actors. All the actors link to a supervisor. So you could think of it as a master actor, but it is it maintains a list of all the actors that it is supervising. It maintains the health of those. It sees that they are completing their work, and if anything wrong happens, then it has a strategy to control them.
So what are the failover chances of the supervisor?
Yeah, so failover chances would be there. So that is why you would be building some redundancy. So the idea is that everything would fail. So you have to kind of work around that. You have to work around a fault tolerance mechanism around that. So for example, even when we talk about high availability, right? That is where we put in kind of multiple nodes in the cluster, saying that okay, I want high availability. So if one node goes down, I still should have kind of another node which takes care of that. So the idea is that that is something that we'll be building in the system. So that is what it is supported, and we have support for that. But how available we want it to be, that depends on how many nodes and how many supervisor redundancies do we want to build in the system.
I mean, this is the design that we have to make in any load balance.
Exactly.
Based.
Exactly.
Nothing specific to.
Yeah. See. Yeah. The only difference, you're right. So the only difference here is that everything is made much easier for you. Most of the design, most of the architectural decisions or the design decisions that you'll be making, that will be based on the product in any case. That for example, if I'm looking at a 999 availability, probably I'll be just putting in 5 nodes. If I'm looking at 7 nines, I'll be putting in 100 nodes. It makes that amount of difference. But so those architectural decisions are still up to you. But then how much you can actually do with the platform, which it is supporting, that is massive in comparison to what we were doing earlier.
Just one. So extending to that question itself. So how is this lookup information stored with Akka? Is there some customization that we can do for?
So customization for
maybe we can start with basically how is this information that you have been using for storing the information for lookups, for distributing the load across all the actors.
Right. So right now what we have been using is the default scenarios. So my messages, they come to the supervisor or my router from where they're routed. Now as soon as they are available to be routed, I actually choose a strategy that okay, my one router has got say kind of 10 actors listening to it. Now I'll tell my router that okay, you do a round robin, because I know that all the actors will be done pretty much in the same time. Now the router actually distributes them round robin, and as well, so it has 100 messages, it will spawn off 10, then it will spawn off another 10, spawn off another 10 to all the 10 actors. What could also happen if I know that my messages which are coming in, they are kind of heterogeneous, and maybe one actor would be swarmed with more work if I follow the round robin. So maybe one message takes 5 seconds to complete, another one just takes milliseconds to complete. Then in that case, I would go for a load balance strategy. So that is where I decide what is the strategy that I want to follow, depending again on the kind of messages which are coming in.
So on the use case basis.
Yeah, exactly. So the idea is that all these things are supported, but on the basis of your use case, you have to kind of define what strategy you want to use.
Just one question related to you said there is one message which takes little more time to process,
right.
Another kind of message takes a little less time.
Right.
If I want to route them to different pools of actors,
Right.
do I have another actor which does that?
So it need not be an actor. So for example, on your logic, you already know that. So probably, for example, it could just be a consumer which is listening to a queue. For example, you have messages which are coming on the queue. There is a consumer which is listening. It need not be an actor, but it is just listening to the queue. As soon as a message comes in, it knows that okay, this is the kind of message, and I know that for this kind of message, this is the pool set that I should go to. Then you will have that okay, heavy work actor, and you will bang a message to that. For another kind of a message, you say, this is just regular message. So you'll have a regular actor and bang a message to that. So that is how you can kind of define your strategy.
Just another, talking this one. So there are various kinds of distributed parallel problems. So like you mentioned Hadoop, and that's data parallel batch oriented.
Right.
So what's the sweet spot for what kind of problem is this a sweet spot?
Yeah. See, like I would say that the sweet spot for this kind of a platform is event based. So anything that you want event based processing to happen and pretty much in real time, which involves a lot of computation, that is where I would use Akka and not Hadoop, for example. But for scenarios where say I'm doing a historical analysis for business information for the past 1 month, probably Hadoop is much better in that case. This one is more of kind of I have my mailbox, send me an event and I'll process it. So for systems like so we actually built a system called fraud detection system, in which you have something like kind of credit card information, and you say for example you make a credit card transaction here in Pune, and in another 30 minutes there's the same transaction from same number credit card in Delhi. So there is no way this can happen unless you are doing it on the web and somebody actually has an online store in Delhi. But that has to be a web transaction. But if it is on a point of sale transaction which is happening within a span of 30 minutes, then it might be a likely fraud case. For those kind of event-driven systems, you could use it in conjunction with something like an Esper, which is a complex event processing system, and then it works there as well.
Just one, sorry.
Yeah, no, go ahead.
So one other thing that, so does it mean that if I have such a real-time requirement,
Right.
but I also need to access data at these actors, is that a good use case, or does data become a bottleneck then?
You want to use the output from the actors.
No, so for an actor to take an action on this fraud detection example,
Right.
it needs to retrieve some data from a data store.
Right.
Let's say compare
Right.
the incoming message with.
Right.
So would that become a bottleneck for that actor?
Yeah, actually that's a very good question, and that is how we are split it. So the answer that I'll give to that one is that, for example, if this actor needs to kind of do 5 things in order to do the computation, you could just, and if those computations can be done in parallel, what you could do is that you could spawn of 5 different actors. Through this actor, like when we saw that an actor can spawn actors, you could spawn of 5 different actors. They are working on your multiple codes. They'll work out in parallel and give you the result much sooner. So for any, so what you want to do is that for any message which is coming in, and if it involves X number of steps, you might just want to kind of divide those X steps amongst X actors to kind of take care of. And then see, the idea is to kind of compute faster. The idea is to be performant, to be scalable, and you can do that only if you can kind of divide work efficiently. If I'm running the entire monolithic block which takes 10 seconds as a sequential process, then it will still probably take 10 seconds even with the actors, because the actor is only doing the same thing. But if you could just kind of divide it and kind of spawn it off multiple cores, it just works, and then you get back the results. Then it is much faster. Okay, how does the fault tolerance work? The fault tolerance works as soon as there is a fault which occurs. Then you can define how do you want the corrective behavior to happen. For example, you could just define that on a pre-start, before the actors are started again, do this, and as soon as the actors are started, do that. So this is what you can do to take care of the fault. So for example, if there was a database connection timeout or blah whatever, and you want to take care of that exception, so you could kind of build in that case here. Okay, there are other concepts that we would not be getting into because Akka is quite a big platform, and it tries to address different needs. It's not that you'll be using all of this just to kind of satisfy a problem, but you could be using different things to cater to different parts of your use case. So for example, there is something called Akka STM, which is Software Transactional Memory. What STM does is that it gives your JVM database-like capability. So you can kind of you can share data amongst kind of various actors through an STM. It gives you all the asset characteristics minus the D. It does not give you durability, but it will give you atomicity, it will give you consistency, it will give you isolation. So that is where you can use STM. So for example, if you have a scenario in which your actors should come back with some result, and I also want the result of that actor, and then I'll do something, or maybe one actor processes on the basis of result of some other actors, then probably you will have to use something like this. But again, as soon as you get into something like this, then you fall into one of the traps that you might not be able to make your system as scalable as you want it to be, because it would not be a shared nothing scenario anymore. So to build a scalable system, you would want it to be shared nothing as much as possible. Then there's something called remote actors, which we talked about, that the actors, like 6.5 million actors, they could either be running on my box, or I could be kind of running 6.5 here and 6.5 there on another box, and I could just kind of call the other 6.5 like the way I'm calling mine. So we just have to kind of bang the message to the remote box instead of mine, and Akka transparently takes care of that. You just have to define the connect. Then there is serialization. Whenever you get into remote actors, you have to get into serialization as well. That how do you serialize the message and send it across? Multiple strategies there. You could use JSON, you could use Scala JSON, you could use Google protocol buffers, the one that we discussed yesterday. So all these things are possible. And then it supports persistence as well. So for example, it connects with the likes of Redis and MongoDB, NoSQL databases, so that you can kind of do your persistence if the need be. For many financial transactions and other things, you might want to do this. So these are other things that are supported. Just feel free to check them whenever you get a chance. But for now, for this discussion, I just wanted to concentrate on actors, fault tolerance, and the three issues like scalability, concurrency, and fault tolerance. So that is what we did in the first part. Okay, I'll just talk about a problem statement that we had to solve, and then probably this gives you some ideas. Probably you have some better ideas that I can incorporate. So the problem statement was that there is a fire hose, or there is kind of a large amount of messages which are coming to us, which do not make any sense kind of when they actually come to us, because we want to process them. So think of it as anything like a Twitter feed or a Facebook feed or anything. What we have at our disposal is that we have these boxes on which we are running Akka, and we just want to process these messages. How does the processing happen? So this is where the processing is happening. It could involve multiple steps, just like you talked that there could be 5 steps that I want to do. So in this case, maybe I want to do some computation, I want to slice and dice, I want to kind of modify, I want to kind of take something else. So just imagine that there are 5 or 6 different steps that you want to do, and every message which is coming in. And finally, you want kind of output not kind of you want to output data, not kind of raw data, but some data which makes sense. So this is the problem statement that we had when we started kind of working on Akka, and some of the considerations were that okay, our process mapping should be simple, so our messages they should be kind of simple. I've just taken out some portion which would have made it made all of you sign some NDA, so just ignore that. But there should not be any master node which is required. I should be able to kind of just plug in my boxes as and when required. Dynamically, I should just be able to say that okay, I need to plug in another box. We should be efficiently using the multi-core. There should be shared nothing. It should be easy configuration, and the last one is self-tuning. So we would not have to care about fault tolerance and garbage collection, actor reuse, actor creation, and all those kind of things. So this was our considerations when we actually started evaluating, and Akka actually kind of pretty much satisfied all these things that we required, and that is how we got to use Akka. So by the way, there is something called Scala actors as well. Like if you look on the internet, actors are defined by multiple frameworks now. So Scala has actors. The web framework for Scala Lift has actors of its own, Akka has actors of its own. But the Akka actors are far superior in terms of performance as compared to any of the others right now. Of course, tomorrow things might change, but the way it is going, they are far superior. And even the strategies that they offer is much more. So on the basis of our requirements, we knew that okay, we do not need software transactional memory. We do not need to go serialization. Sorry, you're not here. Okay. Okay. Right.
One blocking
Right. Yeah. So I'm sorry with whatever I heard. The Apache Mina that you're talking about, that I would compare it to be more with a framework like say Esper, which also does complex event processing. So probably that will be a apple to apple kind of a comparison in my view. Akka is kind of much more than that. It is event driven, and it is kind of taking care of your concurrency and other things as well. So event is just one part of it. So events coming in. So for example, we use Esper for our kind of credit card system that I was talking about. In that, what it also offers is that I could be having these different events coming in, and I could also build a correlation amongst these events with Esper. In Akka primarily, I'll have these kind of millions of threads which are kind of virtual threads which are running, and I should be able to get the parallelism along with the event thing that I'm doing.
I see two use cases for this. One is on the social media side, like Twitter.
Right.
Over there, consistency of data or some events you miss does not matter.
Right.
If it's a transaction based
Right.
data, then missing the event would be.
Right.
So can you experience any loss of events or anything?
No, actually not. Like depends on the loss of events would happen if you do not have enough redundancy built in. But for our case, we did not experience loss of events because there was not just one node which was processing the same events, same messages. There were more than one node. So in any case, if one node was kind of we had a failover. Let us put it that way. But you're right. Like where loss of messages is not a concern. Probably we do not need the kind of failover that we had put in for this one as well. So I don't care, if 50 messages are lost. Maybe I can still gather the sentiment because maybe if there are 20,000 feeds coming in for the same thing, 50 messages lost or 100 messages lost, it's okay. But yeah, for banking transactions, yeah, it'll be a huge loss. But Akka is being used in banking transaction as well. Akka is being used in your telecom billing as well, where every call that you make that actually ends up in being revenue for the carrier. But again, depends on how do you want to build your failover.
The garbage collection causes in some such things matter?
The garbage collection, that will just work the way it is. It would work on the JVM because ultimately everything is going to the JVM. But we haven't seen it, kind of bother us up till now. There are these, kind of so many actors which are running. When they are not in use, they just get garbage collected, and we haven't, kind of faced any problems with garbage collection up till now at least. Yeah, but yeah, that's a good point. Like eventually it could, kind of just become bothersome. Right, exactly. Yeah. Right. Right. Yeah. Especially so in a real-time event, kind of processing system. Yeah, and that is why you have kind of multiple nodes to just take care of the same set of messages as well. So that one, maybe they are not lost, and second, maybe they are still real time. So for example, for the credit card, so we had a similar system that we built for a credit advisory. So there are many companies who actually say, all of us work for a certain company and we are working with, say, IBM, TCS, Cognizant and other companies. Now, I want to look at what are the financial reports which are coming for, say, IBM, TCS and other companies. So if say IBM is defaulting on a payment, I would want to know that whether I should continue doing business with them. So this kind of information needs to be quite real time, because maybe I'm releasing an invoice tomorrow and I see that there is a 90-day default on IBM's payment. So what do I do? So for such systems, yes, real time processing takes in. Okay, so for us, none of this actually, kind of remoting is something that we still might want to consider, but till now we are processing good messages. So for now, it's okay. Okay, the picture isn't complete, but I'll talk. It's nearly complete. Okay, so what we did in our case was that we had everything very loosely coupled. And by loosely coupled, what I mean is we had the messages coming in. So the small dots that you see on the left hand top, those are the messages which are coming in. They actually come into a queue. Now this particular queue is, you can just assume this is a master queue. There are consumers which are listening to it. So in our case, these are the consumers. I've just simplified this diagram a bit. So there are some consumers which are listening to it. Now every message which comes in, that might have n number of steps that need to be done on that message. Some of these steps could only be done in sequence. Some of these steps could be done in parallel. So the way we define our message handling is through a small XML in which we write that, okay, for every message coming in, say for example, do a HTML cleaning first. Then secondly, kind of rip it off of any, kind of strange characters that you see. Third is probably, kind of do a word tag cloud on it. I'm just giving examples. Fourth is that, you select the, top 30 words from the word cloud. Then fifth is do a sentiment analysis on it. So, you could just think of things. And then what you could do is that you could define it in a series of steps which would either run in sequence or parallel. So you say that, okay, HTML cleaner and my, kind of special character cleaner, they run in sequence. After that, maybe, I split it out into parallel of word count and 30 and, top 30 and blah, blah, blah. And then, finally I get back the enhanced message. So you could, define your steps. How it helps is that, if there are steps that you can do in parallel, n steps, you could make use of the, the master worker relationship that you get from Akka. So one actor would be spawning off parallel actors and it will say that, okay, go ahead and complete that. As soon as these parallel actors are done with their execution, they'll actually, kind of, as soon as one of them is done, it will send it back to the main actor's mailbox. Another one is done, it will send it back to the main actor mailbox. Once all the messages have been received, the main actor would just, kind of do a reduce on that and just, kind of send back the final result. So for our, sorry. Right now, yes. Yes, yes. Yeah, that's a good question. So this is something that I was discussing yesterday as well. Somebody else also asked me that, right now since you're running it all on the same box, is it still giving you the same? Actually, for us, we wanted to avoid distribution. So as Martin Fowler says, the first law of distribution is don't distribute. So we just wanted to kind of avoid distribution as much, and we wanted to see that if we are not getting the performance that we are expecting, then probably we'll distribute. So in our case, what is happening is that we were kind of getting all these messages coming in. They were being kind of banged out to the same box, but we were okay. Like the way we are actually parallelizing is that now this is just one box in which all of this is running. There are 6.5 million actors running here. I could have multiple of these boxes, right? So what we did was this. So probably it is the same queue, but I have n number of boxes now. So instead of one box, I have got these 3 boxes. All of them are listening to the same queue, because the messages are coming on the same queue, but I just need kind of parallel processing at a level where I can scale out. So we scaled out and we brought kind of parallel processing there. What I wanted to show you here was that so we are using RabbitMQ, and RabbitMQ now also has a plugin for NoMQ, which speeds up things even further. So this is the consumer actor. Now as soon as the consumer actor sees that okay, there is something that I can do in parallel, I just spawn it off to different kind of workers. Is that a time check? Okay. So I'll just spawn it off to different actors, and then the work gets done much faster. I'll show you some of the results, and the results experience has been phenomenal in terms of sequential versus parallel, even on the same box. So this is how we actually kind of spin out different product instances. So what we can do is that if we see that the CPU utilization is still not enough, on the same box I could spin off 5 product instances also. So 5 of them, they could still be running on the same box, and then there could be 20 such boxes. So the only concern in this case becomes is that we are still reading from a single queue. And RabbitMQ, the way it works is that it hands off, the dispatcher hands off in a single thread. So that is something that we face, that it hands off in a single thread. So you might have multiple queues as well. But those are how much load do you want to handle. Initially we started with something like if we are doing 150 messages per second, we are good. And then once we started seeing the performance, it just kept on going on. And right now we are processing 150 million messages on a daily basis. So it depends on where do you want to go and how much do you want to scale. But if you're ready to kind of scale out or scale up, then it'll just work.
One question: is there a priority that you can define for each actor, saying that there are 2 actors which actually are asking for resources?
Yeah, you can define a priority on the message as well. So for example, how an actor would process a message, that could be prioritized. So if I have got a mailbox which has got 100 messages, 7 of those messages could be high priority. So the actor would process those messages first. But otherwise the actors, you would like them to be workers who are just the same, and depending upon what you tell them to do, you'll just send the message according to that way.
Okay, or is there a way that you can actually define a limit of the resources that
yes, you can do that. Yeah, you can do that. So you can define a limit to how many threads are available to these set of actors, and all those limitations you can kind of. So if you are facing a resource crunch, yeah, you can specify all those things. Just the itself have? Yes, the queue right now in our case it does not. Right now in our case the messages are just coming onto it, but yeah, the queue does not have a failover. We could actually have a redundancy there as well. But the thing is that, and this is what I was talking about, that this is one of the problems that we face. So we have one queue and everybody listening to that queue, and they just kind of, as soon as I throw in the messages to the queue, they just get processed immediately. But RabbitMQ has one thread of dispatch, like it just uses one thread to dispatch of the messages. So that is where we were facing kind of a problem. So what we did was, amongst our blades, we set up pretty much a single queue for every blade. So there is a master queue in which the messages are coming, but then they get distributed onto the different queues, and then the blades kind of take over from that. So that is where we saw some other performance gains. Okay, another problem. Okay, I'll just try to show you a small demo as well. Okay, but before that, another problem that we faced was that we were maxing out on the OS threads. So we had defined a dispatching mechanism for our Akka actors that kind of use the OS threads. But Akka actors were being spawned up and they were getting messages so fast that they were just holding up all the threads which are present on the OS. So we were maxing out on the OS threads. For that there is a dispatcher mechanism in Akka And what that does is, so this is similar to what we talked about. So there is a thread based and event based, and even amongst event based, you could kind of separate them out as priority event based or work stealing. So what happens is that, for example, I've got a mailbox which has got 100 messages, but I'm a slow actor, I'm processing them slowly. There is another actor which has done with the processing of its X amount of messages. So what the work stealing dispatcher would do is that it would steal the messages which are present in my mailbox, which are kind of, because I'm slowly processing them, and it will give it to some other actor. So that even processes it much faster. If one of the actors is slow and its message queue is blocked, then or I'm processing slow, it will take away my messages and give it to somebody else. So all these strategies are built in. Something has. Through RabbitMQ, so once the message is passed on to our actors, through the supervisor, you can know the number of messages in my mailbox. You can also define a limit to your mailbox, saying that none of the actors would have more than 50 messages. By default, it comes with an infinite, so every mailbox would have infinite, but you can define a limit as well. And, yeah, you can define that, and after that, you can define the rejection strategy. So, for example, if the 51st message comes, what happens? Do I discard it? Do I send it to another mailbox? What do I do? Or do I just retry after 5 seconds? So, all those strategies are available. No, you'll configure them. So they are not dynamic. Actually, I'm not sure. That's a good question, but we haven't done that dynamic. But right now they are just kind of configured. You could externalize your configuration, or you could kind of put it in your code. But right now for us it is in the code, depending on the message. Actually, depending on so we have already solved kind of. I would believe that we have solved, but we have solved 2 use cases with this. One is for a similar kind of a Twitter feed kind of a thing, and another is for something called a sentiment analysis, in which, for example, if we go to the likes of, say, I don't know what is a departmental store here, say a Reliance departmental store, and I give some feedback, and then you give some feedback, and somebody else gives some feedback. So this feedback for a day, this is kind of processed in the system for all the chains throughout India, for example. So and then we do a sentiment analysis on that what has been the general feedback on a new promotion that you have done, a new campaign that you have launched, or something of those lines. So, but for that we had to use a different strategy as compared to the one that we use for Twitter-based thing, different kind of tuning to get the optimal results. Okay, just to give you an idea, if you don't split out the messages, for example, what you were asking, if I have got X number of steps that need to be done. Initially, we did not do that. So on an 8-core system, 26 gigs of RAM, heap size of 1.5 gig. When we were processing messages which are not master worker and we were not splitting the steps between the messages, it took 10,000 seconds to process 2.3 million messages. As soon as we went to the situation where we were actually kind of processing messages in parallel, so that came down to 98 seconds. So you can see the difference. 10,000 versus 98. You have so much power which is latent on your machine. You just have to distribute it in the right way. So your steps, if they can be parallelized, that is the best thing. And even on a single box, this is what we are seeing. And once you have so many boxes running around, then there's multiple. I'll just try to see if I can, and I'll probably come back to this.
So this Akka is based on the Scala, and which is based on again the JVM.
Akka is built on Scala,
yeah.
and then but it has a library through Java on which it can be used.
What I want to understand is like when the actors are running actually in the JVM.
Right.
So what is it exactly?
Yes. So the runtime library has to be included. So runtime.
Basically for a Java understanding that actors are not the thread, right? And when they are doing the parallel programming in the end.
Right. So they bind to a Java thread. So what you're saying is right. So they would bind to a Java thread, and that is the reason that even on the JVM, like one thread is allocated what do you call that, size of stack size of 1 megabyte. So you have to. So we had to kind of bring that down, because we knew that we do not require a thread which should require 1 megabyte. We brought it down to a lower level. but that is something that you can define in your kind of Java JVM parameter that this is what you want to do. But eventually, an Akka actor would be getting hold of your JVM thread, which would in turn be getting hold of your OS thread. So that is how these threading would work, and you are bound more by the OS thread as compared to anything else. So there will be a limitation on the number of threads that an OS can spawn, and you would not like to violate that limit. So for all our actors, we always have a thread pool. So we don't mind the actor waiting for some time to get hold of thread rather than kind of maxing out on the OS threads. So for all our parallel computation and everything, we use dispatchers, work seeding dispatchers, and we just specify that okay, you have 2,500 threads for your disposal. So just in case the pool is full and all the actors are using all the 2,500, then they just wait for a while as soon as one is free. But we just leave ourselves to that selected OS pool of threads. Okay, I'll just try to show you if it works. Normally when you're doing a demo things crash, so I don't know. Okay, so maybe what I'll do here is that so I'm starting one of the product instances, so so that we can actually send messages to it, and then you will be able to see that okay, once the messages are coming in, how they are processed. Okay. Okay, so you see, I submitted 10,000 messages, and those 10,000 messages just got processed like that. What we could do is that, for example, I just kind of start another instance of the product. I'll just start 2 this time. Just close this one. And I'll start over. So you see now both of them start processing because we are picking up from the same queue. So both of them just start processing and they get done, probably not in half the time, but much faster. I could just go ahead and kind of start spinning instances, but my feed is still coming from the queue, and there are multiple. I'm achieving parallelism on the same box. The idea is to use as much of CPU, as much of threads that I can use on my multi-core system, and then I can kind of use multiple boxes as well. So I'll just to close our terminals for now. We'll just get back to this. So again, we were here. So this is what I talked about. It's an a la carte. There are many kind of features which are available. You just might want to use the ones that you are interested in. So remoting, if it works for you, yes, use that. STM, if it works for you, use that. Something else doesn't work for you, don't use that. For us, the only things which worked were kind of access and fault tolerance, and that is what we use. Where it is being used, it is being used in kind of all these places. So you talk about the place, maybe transaction processing, kind of simulation, batch processing, gaming, business intelligence, complex event processing. So it's being used in all these places already. So it's production worthy. People are using it in production. You just have to kind of find your use case of parallelism and kind of implement that. It takes away your concerns about threading and concurrency failover. So that is where it helps you. This is, by the way, from the Akka side itself. You can find more use cases. So right now this is the latest version, 1.3 RC1. 1.3 RC2 is due this weekend. To get more information about the product, you could actually kind of visit our blog site with the tag Akka. So there we talk about more details of whatever I've talked about. And that is it. Any questions? Number of cores.
How's the behavior? Is it you see a linear kind of behavior?
do I see a linear performance improvement on the number of cores? Yeah, actually, I would expect to. But what happens is that there is kind of a lot of differences which happen. So, for example, if you try to thread out a lot, then there is an overhead on that as well. You need to kind of find a sweet spot. So it would not be that if you have 2 cores, you just get half the time, but it becomes better. And sometimes if your job is so small and you're still threading it out and you're kind of reducing it, it just becomes a bigger overhead. So depending upon the job, you have to kind of define how do you want to distribute it. Actually, I have an interesting blog on the site as well where my system, and I was comparing it with my colleagues, and he has a MacBook Pro with half the number of cores, but still the processing was going on faster there. And so I couldn't find a reason, and then we figured out that on the MacBook Pros by default they are shipped with hyper-threaded cores. So that means that it can run 2 threads at the same time as compared to one on my machine. So it is pretty much being the same thing. So I'm having 4